Hello, welcome to Lecture 8. In our last lecture, I invited you to rub a balloon against your head and try and make it stick to the wall and see if you could make it stick. In today's lecture, we'll start by talking about how that works.
To answer our question about why a charged balloon will stick to a neutral wall, we'll talk about polarization, and this is charging without transfer of charge. So to start our problem, we charge up our balloon by rubbing it on our head. That means our balloon acquires a bunch of negative charge. Okay, so we'll start by putting some negative charges on the balloon, and then we take the balloon and we put it close to the wall. Now, let's think about what a wall is made out of. A wall is made up of molecules, and molecules tend to have a positive end and a negative end. If your wall is neutral, then those molecules are more or less randomly organized all over the place. And that random organization leads to the wall being overall electrically neutral. All the pluses cancel with all the minuses. But the surface of the wall, that's an interesting place. So right at the surface of the wall, we have all these molecules with a positive end and a negative end. The molecules at the surface of the wall will flip over. The positive end is attracted to the negatives of the balloon. So at the surface of the wall, they all flip, they all line up. And in fact, that's what polarization means. Everything is turned one way. So all the molecules will turn so that the positive ends are close to the surface of the wall. They're attracted to the negative balloon. And all the negative ends are turned away from the surface of the wall because they're repelled by the negative. This results overall in the surface of the wall being slightly positive, and the negative balloon is attracted to that slightly positive surface. A couple of things to mention here is that the polarization force, this attractive force due to polarization, it happens because the charges in a neutral object are slightly separated and lined up. It's not because the objects are overall oppositely charged. So the polarization force always happens between a charged object and a neutral one, and it's always attractive. So now let's talk about that force. We saw that our charged balloons, they repel each other, and that's due to an electric force. The electric force is given by Coulomb's law. Coulomb studied the interaction in the 1700s. For sure, he's not the only guy who studied electric forces. All of the cultures knew about charge, and they probably all measured the force. But more or less, mostly the Europeans of that time got in the books. So Coulomb used a torsion balance, similar to the one used later on by Cavendish to study a gravitational force, and he was able to more or less put the charged objects on a balance and measure the force, which is pretty interesting given that it was the 1700s. Okay, so let's see what Coulomb found. He found that if we have two like charges, so two positives or two negatives, they're going to repel each other. So let's draw those forces first. So let's label our charges Q1 and Q2. There's a force on charge Q2 that's repulsive. That means it's pushed to the left. And we label that force by charge 1 on charge 2. We won't keep this notation up forever, but it is pretty useful in the beginning. Now, then there's two ways to think about the charge on Q1. First is Newton's third law. If charge 1 pushes charge 2 to the right, then charge 2 is going to push charge 1 to the left. Let's draw that force. F2 on 1. So Newton's third law says that for every force, there's an equal and opposite force. Also, the charge Q1 is positive. It's repelled by charge Q2. So there's two ways to think about that force. Coulomb also found that the magnitude of this electric force, it's inversely proportional to the square of the distance between the charges and proportional to each charge. So let's write down the equation for the force. The magnitude of the force, so I'm writing it without a vector sign because now we're talking about magnitudes, is a constant k times the magnitude of charge 1 times the magnitude of charge 2 divided by the distance between them squared. And I'll just highlight this up here. The charges are a distance r apart. Got to be careful here. Some people actually fall into a little trap of thinking that r stands for radius, and they take every distance they're given and divide it by 2. I think that's just a habit left over from a math geometry class. In physics, we very often refer to r for distance. So we don't use d, we just use r. So on our diagram here, r will be the distance between the two charges. Okay, really important to keep that straight. And second, I know I said it, but I'm going to point it out as well. Since our equation gives us the magnitude of the force, we always use the magnitude of charges. So whether the forces are charges are positive or negative, always put in the positive. Because we're calculating the magnitude of the forces. Okay, this is true for our negative charges as well. If we have charge Q1 and Q2 that are both negative, separated by a distance r, then there's going to be a force on charge 2 from charge 1 to the right, so force of 1 on 2. There's an equal and opposite force of 2 on 1. All right, so now a comment about that K that I wrote in my equation. The symbol K stands for what we call the Coulomb constant. It has a magnitude of 8.99 times 10 to the 9 with units of newtons times meters squared over coulombs squared. This Coulomb constant K is also given by 1 divided by 4 pi times epsilon naught. Epsilon naught is another constant, and that constant is called the permittivity of free space. It basically describes how light waves can get through a vacuum, or electromagnetic waves get through a vacuum. The value of that constant is 8.85 times 10 to the minus 12 coulombs squared over newtons times meters squared. For what it's worth, I don't care if you write your force as 1 over 4 pi epsilon naught Q1 Q2 over r squared or K Q1 Q2 over r squared. Both are fine. Okay, so our like charges have repulsive forces, and our unlike charges, our opposite charges, have attractive forces. So if we have two charges, Q1 and Q2, one is positive and one is negative, then the force of 1 on 2 is attractive. It pulls it to the right. Force 1 on 2. And the force of 2 on 1 is also attractive. Force 2 on 1. So like charges repel, unlike charges attract. What's really important here, what I'd really like you to take away from here, is that we use the equation to get the magnitude, to get a positive answer, and you use your common sense to get the direction. So you get your numbers from the equation, you look at your picture, you ask yourselves, do these attract or do these repel? What direction do I mean by attract or repel? And that's how you get the direction of your vector. Now, here's a good question. How big is the electric force? So, to answer that question, let's look at an electron and a proton where the electron circles the proton. So this would be the case of a hydrogen atom. And we know lots about the hydrogen atom. We know that in the atom, the electron is a distance r away from the proton, and that distance r is 53 picometers, where a picometer is 10 to the minus 12 meters. We know the charge on an electron is negative e, so minus 1.6 times 10 to the minus 19. We know the charge on a proton is plus e. And we know the mass of an electron, 9.11 times 10 to the minus 31 kilograms. And we know the mass of a proton, 1.67 times 10 to the minus 31. For what it's worth, I probably wouldn't expect you to know these numbers off the top of your head, but I would expect you to know that these are things you can look up. For an electron and a proton, you certainly have to remember that the proton is positive and the electron is negative. Okay, let's go ahead and find our electric force first. So the magnitude of our electric force is our constant K times the charge on the electron, the magnitude of that charge, times the magnitude of the charge on the proton, divided by the distance squared. So that's K times E squared over R squared. K is our Coulomb's constant. That's 8.99 times 10 to the 9 newtons meters squared over coulombs squared. If you put this through your calculator, what you get for your electric force, the magnitude of your electric force, is 8.19 times 10 to the minus 8 newtons. And of course, the direction of the force is attractive. This force is tiny. Okay, that's a little small force. Slight sidetrack. Do you think you could use this force and find the speed of the electron going around the atom, the proton? Okay, so there's our electric force. Why don't we label that electric? What about our gravitational force? We know that any two objects with mass do experience an attractive force. And that attractive force is given by F equals g, the gravitation constant, times the mass of the first object times the mass of the second object, divided by the distance between them squared. G, our gravitation constant, that's given by 6.67 times 10 to the minus 11. That's newtons meters squared over kilograms squared. And that gives us, for a gravitational force, the magnitude is 3.6 times 10 to the minus 47 newtons. So if the electric force is tiny, then this gravitational force is pretty much not there at all. So let's compare them. Let's divide. So let's find the ratio. So let's do the ratio of the electric force over the gravitational force. 8.19 times 10 to the minus 8 newtons divided by 3.6 times 10 to the minus 47 newtons. That gives us an answer of 2 times 10 to the 39, 2 times 10 to the 39. That is so much bigger. So the electric force is about 10 to the 39 times bigger than the gravitational force. Okay, that's a pretty interesting result. This tells us that the force of gravity really only applies when we're talking about big things like the Earth and the Moon or the Sun and Jupiter. So it's when we have big things that the gravitational force is significant. Our electric force then pretty much accounts for everything else. The strong and weak forces, those are nuclear things. We don't experience those really on a daily basis. So all the other forces that we treated as separate back in physics 1050 or 1020, like friction and normal and pushing and tension forces, those are all really just the electric force in disguise. I think that's pretty interesting. On a practical note, what this means is that most of the time when we're talking about electric forces, we're going to be neglecting gravitational forces because for the most part, those gravitational forces are just so small compared to the electric forces. So let's get some example drawing the forces now. So for the first question, the charge of sphere 2 is twice that of sphere 1. So this has charge Q1, this has charge Q2, which is equal to 2 times Q1. Draw the vector which shows the force of 2 on 1. Okay, so let's use a Newton's third law approach. Newton's third law tells us that the two forces will have equal magnitude and opposite direction. So my force of 2 on 1 is going to point to the left and it's going to be the same length. Now, if you preferred a Coulomb's law approach, you could write each equation. The force of 1 on 2 is K times the magnitude of Q1 times the magnitude of Q2, which is 2Q1, divided by R squared, where R is given as the distance between the charges. And then if you apply the same equation to F of 1 on 2, you get K times charge 1 times charge 2 over R squared, and you know it points to the left because it's a repulsive force. Okay, so two strategies for that one. Part B, draw the vector that shows the force of 1 on 2 if the distance between the spheres is reduced to R over 2. So this problem has the same parameters as this problem, but we now only have half the distance. What does that do to the force? So we know that the force is going to be repulsive. Our distance is R over 2. Let's see what R over 2 does to our equation. So force of 1 on 2 equals K times the magnitude of Q1 times the magnitude of Q2 divided by R over 2 squared. Now, R squared over 2, or R over 2 all squared, is R squared over 4. So to write our equation, we've got K times Q1 times 2Q1. In our denominator, we have R squared over 4. So we've got an R squared in our denominator. Now, where we have R squared over 4, we have a denominator of a denominator goes up in the numerator. So we've got 4 times the force from the first one. So our force for part 2 is 4 times as long as our force for part A. So if you half your distance, your force increases by a factor of 4. Okay, last part, and I'm really going to suggest you try this on your own first. Draw the net force on the charge at lower left. So draw the net force on Q3. Now, here's a place where a lot of students get into a hiccup with drawing these forces. I strongly suggest that you hit pause, grab a sheet of paper, and you draw the forces first. If you're one of the ones who might run into this hiccup, let's get that out of the way right now so you wouldn't make the same mistake on the test. Okay, you hit pause and give it a try, and I'll move on to the next slide and draw the answer there. So before I draw the correct answer, I'm going to go ahead and draw the wrong answer. So this is how not to draw the forces on the lower left charge. So this is how we do it wrong. So when people look at this problem, they definitely think about it correct. They look at this, they look at charges 1 and 3, and they say, oh, those are two positives, they repel. That part is right. Here's the part that's wrong. They put an arrow on Q1. Then they look at charges 2 and 3, and they say, oh yeah, they repel. And I even notice Q3 is pretty big, so I'm going to draw that force as bigger. And they draw a force on Q2. Then they look at Q4, Q3 and 4 are positive, they repel, so I'm going to draw a force like this. The reason that this is wrong is because you had to draw the force on the charge at the lower left. You have to draw the forces on Q3. On this picture, there are no forces drawn on Q3. There's a force on Q1, there's a force on Q2, there's a force on Q4, but there's no force on Q3. So that's the key. You must draw arrows on Q3. If it helps, think about the fact that you're drawing a free body diagram of charge Q3. So all the forces have to go on Q3. If I ask you this question on a test and you give me the diagram that's on the screen right now, you're getting 0 for your force vectors because you haven't done what the problem asked. Okay, now let's have a look at what that answer should be. So if we look between 1 and 3, those are like charges. So charge 3 is repelled by charge 1. That means charge 3 is going to be pushed down because of charge 1. I'll label that force of charge 1 on 3. Okay, let's do 3 and 4 next. Those are like charges, so Q3 is going to be pushed to the left because of charge 4. 1 and 4 have the same distance and the same charge So the force would be the same size. Force of 4 on 3. Okay, 2 and 3, those are separated by some distance. Q2 is pretty big, so it's going to be a repulsive force. So Q3 is going to be pushed left and down because of Q2. It's a little bit hard to tell what that size of that force is going to be. I'll draw it about this long. So force 2 on 3. Okay, so we were asked for the net force. The net force would be the vector sum of all these forces. So we have a force going left and a force going down. We have a force left and down. So our net force is going to be to the left by a bit, and it's going to be down by a bit. So our net force will look something like this. And I'll label that F net. Okay, so that's how you would correctly draw the force on charge Q3. As a homework example, and we're going to go through lots of examples on this on the following slides, I'll give you the magnitude, I'll give you the charges of each of the 4 charges and the distance of one side of the square, and you find the magnitude of each of the forces we drew above. More examples of this will be coming up, so if you can't quite do this problem, this homework problem yet, it's okay. Maybe look at the following slides, then come back and do the problem. I will post the answers here with this part of the notes though.